Hi there, folks. Today we're looking at interval notation, and that word interval, if you've never heard the word interval before, it's kind of like a space designated by numbers almost. So like an interval kind of tells us to go from one spot to another spot, or one point to another point, or one value to another value, okay? That's an interval. And when we talk about intervals, when we go from one value to the other value, we cover all the values in between. So if I said, hey, we want to go from 1 to 5 on the number line, the interval would be 1 to 5, and it would cover 1, it would cover 5, and it would cover all the numbers in between, all right? We use interval notation as a kind of a shorthand pretty much for inequalities. Anything that we could express with an inequality, we can express with interval notation instead, but interval notation kind of summarizes everything we need from the inequality. For example, if we look at the inequality A less than X less than B, that's an and inequality that's describing the space between A and B, all right? And so when you think about that, it's describing an interval on the number line. And so an easier way to express it, or a faster, a shorthand way to express that, is instead of using all these inequalities, saying, hey, I want to be above the A but less than the B, so really I'm shading everything in between, is I just label it in terms of the starting value and stopping value. I just say, hey, start at A, go to B, and use everything in between. And so that's kind of how interval notation works, where they're just listing, hey, this is where it starts, this is where it ends. And then our way of expressing the equal to versus not equal to condition is this idea of using a parenthesis versus a bracket. So here with no equal to conditions, I use a parenthesis. It means, hey, I want to go from A to B. I'm going to use all the values in between there, but I'm not actually going to include A. I'm not actually going to include B, all right? Likewise, when I look at the second one, A is less than or equal to X, less than or equal to B, once again, it's saying, hey, start here at A, go to B. So I go from A to B on the number line. I use all the values in between, but I also include A. That's what the bracket tells me. I can actually equal that value. I also include B, all right? And so if I kind of extended this just a little bit and said, hey, what if I had A is less than or equal to X, less than B? Notice there's no equal to condition that second time. Well, the way to express that would be, hey, I go from A to B, so I include all the values in between. I include A, but not B, all right? I can equal A, but I can't equal B. And so we use interval notation. It's just a shorthand. It's a really nice, succinct way of writing these inequalities, okay? For example, if I look at something like this guy, and, if it helps, we could draw this on a number line first. So like something like this guy, I could take it off to the side and say, okay, ready? I'm going to go from -3 to 11. If I think about this on a number line, I would have a closed dot at each of these, and I would shade everything in between. And so if I just kind of go from least to greatest, if I listed this as, hey, where does it start, where does it end? I would just say, hey, you know what? The shading starts at -3. So I'm going to say, hey, the shading starts at -3, and I put a comma and say, and it ends, so I start shading at -3, and I keep shading until I get to 11. And now I have to tell you a little bit about what can happen at the value of -3. See, really, this is telling me everything in between there counts. So 0's in there, 1 is in there, 2.5 is in there, okay? I'm showing you that I'm going from this value to this value, so all the values in between. Now let's talk about those actual values. I would say, hey, you know what? I'm going to include the -3, so I could equal the -3. That's part of the shading. And I'm going to include the 11. That's also part of the shading. And so a nice way to rewrite this guy, instead of using the inequality, I can use interval notation, okay? This one, same kind of thing. Again, if I were to express it on the number line real quickly, and you're probably looking at this going, I think I could do it without the number line here, Mr. Jansen, but I just want to do one more with the number line because it's fun. Here's an open dot, here it's a closed dot, and I would shade everything in between. That's the graph of the inequality. So if I were to describe the shading, least to greatest, I would say, hey, you know what? I start shading at 5, and I stop shading when I get to 11. So that's the interval. It goes from 5 to 11, and I use all the values in between. But now when I talk about the 5, I say, well, I can't actually equal the 5. The 5 isn't part of the shading, okay? The shading starts at 5 or immediately after 5, but I don't actually include the 5. But I do include the 11, okay? So the 11 is part of the shading because of that closed dot, okay? That equal to condition. But again, that's just a nice way to express an interval of values, a section of values. And we used to use inequalities for that. Now we can use interval notation. If I look at the next one, again, without actually shading this thing, without actually putting it on the number line, think about where it is on the number line. Essentially, this is telling me, hey, this is going to start at -5, and it's going to stop at +1. So my interval goes from -5 to +1. So I use all the values in between there. And then the -5 is part of that shading, but the 1 is not part of the shading. There's no equal to condition. Okay, so there it is in interval notation. Okay, it's just another way to express these inequalities. If I look at this one, same kind of thing. It starts at 3, it goes to 6, so I would shade everything from 3 to 6. So I say, hey, it starts at 3, and then I shade everything all the way up to 6. But the 3 isn't actually part of the shading. I really start right after 3. And the 6 isn't part of the shading. I stop right before 6, okay? And so I use those parentheses to indicate that there's no equal to condition. And here's maybe the downfall of interval notation. When you look at this, you see 3, 6 in parentheses, you're probably thinking it's an ordered pair. You're thinking a point, all right? And the only way to distinguish whether or not you have an ordered pair or whether or not you have interval notation is the context, okay? We can only tell that this one is interval notation because of the context of this particular problem, because I just rewrote a compound inequality, all right? If I was looking at a graph and said identify that exact point right there, well, then I'd know that this was an ordered pair. So we really just have to be careful with the context. And the reason I mention that is because when we start to talk about the graphs of polynomial functions, you're going to see interval notation and points written side by side, and it's really important to understand which ones are interval notation and which ones are points, based on the context, based on the things we are talking about, okay? If I look at this one might be a little bit tricky without the number line at first, so let's draw a quick graph of this thing. So here I've got 4, and I want to be less than or equal to that, so I would use a closed dot, and I would shade everything to this side. And so when I think about, again, I want to go least to greatest, think about where this thing starts. Well, this thing keeps going to the left forever. I keep shading that way forever. So the value, quote unquote, at which it starts would be -infinity. Okay, and so we're introducing this idea of infinity. If I go to the left forever, well, the value out there is -infinity. Okay, that's forever in the negative direction. So this one starts, if it's possible to get to a starting value, the starting value would be a -infinity. And so if I start at -infinity and I shade all the way up to 4, I would express it this way. And so here's the thing. The thing you need to understand about infinity isn't really a number. It's more like a concept of a number. We can't ever actually get to the value of infinity. But it's this kind of concept of a value if I could go out there forever. See, it's that hypothetical, all right? I can't go that way forever, but if I could, I would end up at -infinity. And so the idea here is we could keep going that way forever. We're never actually going to get to -infinity, but it's the concept that it's out there somewhere, all right? And so stating it that way, when you think about whether to use brackets or parentheses here, I can't actually ever get to -infinity. It's an idea, it's a concept that's out there, but I can never actually equal it. So anytime we have an infinity or a -infinity, we'll use a parenthesis, okay? We can never actually equal that because it's not a true number, it's a concept of a number, okay? And then the 4, well, that one I can equal, and that one is part of my shading, okay? If I look at the next one, same kind of thing. Let me draw a quick sketch here. So I've got -1, I've got a greater than -1, open dot shaded this way. And so this one, if I go left to right from least to greatest, I can see the smallest value. The smallest value is -1. But then the biggest value, this thing keeps going forever. And so I can't ever actually get to the end of this thing. But if I could get to it, if I was able to get to the end would be at +infinity. So again, it's that idea of talking about this in terms of a hypothetical. If I could get to the end, I would be at +infinity, okay? And so there's my symbol for infinity once again. There's no equal to condition for the -1 because there's no shading there, and I can never actually equal the +infinity, so that one also gets a parenthesis, okay? But again, it's this concept of a number. If I could go forever, then I would be at infinity, all right? This one, same kind of thing. Once again, I have a greater than or equal to negative 8. So if we kind of visualize the graph in our heads, that one would start at negative 8 and go up forever. So in terms of the interval, I would say negative 8 to positive infinity. And once again, equal to condition for the negative 8, parenthesis for the infinity. This next one, it says less than 7. So if I shaded less than 7, that's shading to the left, which means this one keeps going to the left forever, which means my starting value, quote unquote, all right, if I could go to the left forever, I would start at negative infinity, and I would climb up to a maximum value of 7. Okay? And once again, parenthesis for the negative infinity, because I can't ever actually equal that thing. Parenthesis for the 7 this time because there's no equal to condition. Okay? And if it helps, draw the graph of this thing or visualize it at the very least. Okay? Now, if you've noticed, there's one kind of inequality we haven't talked about. That's an OR inequality. So if I have two chunks of this thing that are split up, I essentially just write it as two separate intervals, and then I put a union symbol in between those intervals. It's just a big U, all right? And so if I have separate chunks, it's really just, hey, let's write the interval notation for each of these pieces and then put a union symbol in between to say, hey, we've got this chunk covered, but we also have this chunk covered, okay? And so when you look at this, it looks kind of strange as we're staring at this in terms of math speak here. But in practicality, if we understand interval notation, the practical aspect of this, when we actually go to do an example, is really easy, okay? It's just writing the interval for two separate inequalities and then putting a union symbol in between. For example, if I look at something like this guy, I've got x is less than or equal to a negative 2. And so, again, if I were just ignore the second half of this thing, if I just ignored that and said, hey, let's write the interval for this, less than that negative 2, that's shading to the left forever, that would start at negative infinity and go all the way up to negative 2. And I'd have a parenthesis here and a bracket here because I can't equal the negative infinity, but I can equal the negative 2. Okay? Now let's pretend for a moment that we didn't ignore any of this stuff. Okay, so let's ignore the first half of this thing. Let's ignore what we've done so far. Let me cross it off. If I just had x as greater than 5, well, that would be an open dot and then shaded to the right. That would mean I would start at 5 and go up forever, so go up to infinity. Once again, parenthesis for the infinity, parenthesis for the 5 because there's no equal to condition. Okay? So I'm just doing those two separately. Well, let me stop ignoring things. I just slap a union symbol in between here. Okay? It's basically saying, hey, I have two separate chunks. Chunk 1 goes from here to here, then I skip some stuff, and then I go from here to here. So I have two separate intervals that I want to graph together, okay, that are part of the same thing. All right, and that's why we use that union symbol. If I look at the next one, again, ignore the second half of this. If x is less than 3, that would go from negative infinity to positive 3. No equal to conditions. X is greater than or equal to a 10 would start at 10 and go to positive infinity. I could equal the 10, but I can't equal the infinity. And because I have two separate pieces, I just slap a union symbol in between. All right? And it's really important that you go from least to greatest here. I can't write this as like 3 to negative infinity. That's backwards. It's negative infinity to 3. It's always least to greatest. And even the intervals, the two separate intervals, I have them from least to greatest. Okay? If we look at something like these guys, just find the domain and range. We're used to writing domain and range, expressing it in inequalities and that kind of thing. But let's just use some interval notation here. So if I look at something like this guy, keep in mind there are arrows on the end of this. Maybe you can't see them. I'll make them a little bigger. So there's arrows on this thing, so that continues forever. And so if you think about domain is the left and right. If I look at this thing going from left to right, well, it goes to the left forever. And it goes to the right forever. So if I was expressing all the x values that are covered by this function, all the x values that are used by this function, well, the function continues forever in each direction. I would just say, hey, this thing for the domain, it goes from negative infinity to positive infinity. I'm just talking about which x values are covered, okay? And so again, when you look at domain, you have to think kind of one-dimensionally, all right? The graph is in 2 dimensions, but if we think one-dimensionally, if we only think about x, if we only think about how far the function travels, which values are covered from the perspective of x as the function goes left and right, well, the function goes left forever and the function goes right forever. And the function, if you think about the values that are used here, this function will utilize every x value on the graph, okay? And so the domain is negative infinity to positive infinity. It's all real numbers, okay? The range then, well, the function doesn't use all the y values. Again, think one-dimensionally. If I just look up and down, all right, well, the function doesn't use all the y values. Yeah, it goes up forever. I can see that from the arrows, but it doesn't go down forever. The lowest it goes is -2. And so if I'm talking about interval notation, I have to go least to greatest. So if I think about the smallest y value that gets covered here, it's -2. So think about the function from the perspective of y. It starts at -2, and then it goes up forever, so it goes to positive infinity. And yes, we have an equal to condition at the -2. That's where the vertex is, and a parenthesis at the infinity, because I can never actually equal that thing, okay? If I look at the next one, once again, I have arrows on each end of this thing. They're not written real big, so I'll make them a little bigger here. But here's a parabola, and the parabola follows the same kind of rules as if I look left and right. Think about which x values are being covered. The parabola keeps getting wider and wider and wider as we go, so once again, the domain is all real numbers. And we're used to stating it as all real numbers, but in interval notation, I would just say, hey, all real numbers just means you go from negative infinity to positive infinity, okay? The range on this one, once again, the lowest point here looks like 1, 2, 3, 4, -5. So this one starts at -5 and then goes up forever, so -5 to positive infinity. And normally we'd write that as like y is greater than or equal to -5. And we just say -5 to infinity. I can equal the -5, it's part of my vertex, but I can never equal infinity, okay? If I look at this one, a sideways parabola. We haven't seen these before, but maybe we will someday. Hint, hint, wink, wink. And so if we look at something like this guy, this sideways parabola, again, there's arrows on each end, but think about left to right. Does it go to the left forever now? Does it go to the right forever? Well, yeah, it goes to the right forever, but not to the left forever. Notice, to the left, it kind of gets capped off at 1, 2, 3, 4, 5, -6. So the furthest to the left that this thing goes is -6. So the domain goes from -6, but then from there it does go to the right. From -6, it goes to the right forever. So it goes from -6 to infinity. And again, equal to condition here, that's almost like the vertex, quote unquote, and parenthesis here because I can't equal infinity. But now look at this. Think about y. Well, now look up and down. If this is truly a sideways parabola, we know the parabola is going to get wider and wider and wider. Well, that's covering more and more y values now, because as it gets wider, it's increasing up and down, okay? And so when we think about this thing, the range is going to be all real numbers. It does go up forever, and it does go down forever. So negative infinity to positive infinity. If I look at the next one, this one kind of looks like half a sideways parabola. Looks like it starts here, and there's an arrow on this end. It's hard to see. But if we thought about this as like half a sideways parabola, let's talk about the domain. Again, it doesn't go left and right necessarily forever. So I think about it and say, well, it does go to the left forever, okay? And if it goes to the left forever, I want to start at the smallest value. That's left forever. That's negative infinity. But it doesn't go to the right forever. As I go to the right, it starts at negative infinity. And then the function exists from negative infinity all the way up until I get to an x value of 3. That's where the function stops, okay? And we can't equal the negative infinity, but it looks like we do equal the 3, okay? And then the range this time, again, we look up and down. We say, hey, does it go up forever? Does it go down forever? Well, if it's truly half a sideways parabola, it's going to keep going up forever because that half is going to keep getting bigger and bigger like the parabola is getting wider. So it is going to go up forever, but it doesn't go down forever. It stops. And so when I look at this from least to greatest in terms of the y values, the smallest y value that's on this graph is a positive 2. But then from there, the function goes up forever, so to positive infinity. And it looks like it equals the 2, but I can never equal the infinity, okay? If I look at something like this guy, I don't have the graph drawn, but I understand what the graph looks like. And I don't need an in-depth graph of this thing, all right? I understand right away when I look at this, this is a parabola. It's got a vertex. So the vertex on this one is 2, -4. And it opens up because the a value right here is a 1. And so if I just think about a quick sketch of this graph, 2, -4 is down here, and it opens up. And the thing we should realize by now with parabolas, if it's in the formats we've been dealing with, if it opens up or down, well, it's going to continue to get wider and wider and wider. So when I think about the domain, well, this one's going to go to the left and right forever. So the domain, it's all real numbers. It's -infinity to +infinity. But now the range hinges on the vertex. The vertex was the maximum or minimum. In this case, it's the minimum value. So the lowest value I get is -4. That's right from the vertex. And sorry, that's going to be a closed dot. Or sorry, an equal to condition because it's part of the parabola. I can see it right there. It's the vertex. See, that's the smallest value, but then it goes up forever from there. So +infinity. Okay? And if I look at the next one, once again, I don't have to get a super accurate graph of this thing. Just draw a sketch of the graph. If you think about a sketch of this graph right here, it's got a y-intercept of 1 and a slope of -2. There we go. There's the graph of this thing. And so if I think about this thing going left to right, well, it goes to the left forever and it goes to the right forever. So the domain is all real numbers. In interval notation, that's -infinity to +infinity. And the range, when I look at this line, once again, I understand that it's a line, it's a linear function. It goes up forever and it goes down forever. So when I think about all the y values on this graph, it's all of them. It goes up forever and down forever. So the range is also all real numbers. So -infinity to +infinity. Okay? So again, interval notation is just a nice way of expressing where something exists, whether that's an inequality, whether that's domain and range. But it just lists it as this is where it starts and this is where it stops, least to greatest, okay? And everything in between. And then we use parenthesis for no equal to condition and a bracket for an equal to condition, okay?